Hello students, in this video we'll discuss the Cholesky factorization of a matrix. Let's suppose that T is strictly positive definite meaning of course that if I do the inner product of T, V with V for any vector V, not only do I get a non-negative inner product, but I get a strictly greater than zero inner product, right? And so for these positive definite operators or matrices, we know that every eigenvalue, that the spectrum of T, a set of eigenvalues, is contained in the open interval from 0 to plus infinity, like so. And I can't get 0 now, because if I got 0, this says the norm of TV is greater than 0, so there's nothing in the kernel except for 0 itself, right? For V not 0, right? Right? Excellent. Okay, excellent. So what we're going to do now? So that's what the spectrum's contained in. So now these things also have positive, then T has a positive definite square root. Okay, and indeed, how do we see that, of course? Well, we know that we can diagonalize T, right? So in other words, if I look at the matrix representation of T, I know that T can be written in this form over here as a matrix, as a P, and then a D, and then a P inverse, where all the elements on the diagonal entry of D are strictly greater than 0. And this says that, of course, the positive square root of T over here, we're going to use this notation, would just be P square root of D, just the positive square roots of the diagonal entries, P inverse over here. Great. And so now, we can also, therefore, we can factor this as self-adjoint. So this tells me that T is equal to what? T is equal to, let's say, S star S, where this thing over here is our S star, right? So that's just the square root operator, okay? And so now what's the trick behind this? The trick behind this is that I'm going to apply the QR factorization to this matrix over here, S. So let's apply the QR factorization to S, the square root. And so what would that give me over here? That would give me that S is equal to Q, an orthogonal matrix, times R, an upper triangular matrix, okay? And now I know that, and what I'd like to show is I'd like to show that all the elements of the diagonal of this upper triangular matrix are non-negative numbers, okay? And that just follows from the symmetry, right, by the positive definite assumption. Okay, and so now what do we want to plug in this formula? Now apply this to T, apply this to T. If we apply this to T, we have that T is equal to S star S, but S is Q times R, so this is QR star. And then what? It's QR star and then QR. By the involution property of the adjoint, this becomes R star Q star Q R. But now I know that this is the identity over here because it's an orthogonal matrix over here. So this is just the identity over here by orthogonality. So this is just going to be R star R. So we have over here is we've just written R. So we've just written T as R star and then R like that. And so now, of course, I have the upper triangular, lower triangular decomposition over here, this upper triangular matrices, right? So this is upper triangular, right? This, of course, is lower triangular, so this is our Cholesky factorization over here. This is called the Cholesky factorization. Okay? And this, of course, Cholesky factorization is unique, right? So this is a unique factorization. So this factorization, so remark, this factorization is unique. And of course, what are the diagonal entries of R? Here, the note is that the diagonal entries of R, so R is really Rij, right? And Rii are strictly greater than over 0 over here by the fact that it's a strictly positive definite. This follows from strictly positive definite. Okay? This representation is unique. By the uniqueness of the QR factorization. Okay. And one other remark actually is the following. The other remark to make over here, so that's remark 1 or remark 2. Oftentimes in text you'll see this factorization written in terms of lower triangular instead of upper triangular. This can be written in terms of lower triangular matrices too. Okay. And the idea is that oftentimes in numerical analysis books, you'll see the Cholesky factorization written in terms of lower triangular matrices just for the efficiency in terms of trying to solve, use Gaussian elimination to solve the system in the backwards order over here. But in this case, it's sort of more natural to use the QR factorization because we're really in a very useful way of implying the positive definite part of this thing. Now, the positive definite part of this thing allows me to compute a square root, and then the QR factorization over this thing is always going to put things in terms of the Gram-Schmidt, or we're always using orthogonality in this sense, and so the orthogonality in Gram-Schmidt is constructing an upper triangular matrix, right? And so we're going to exploit that upper triangular structure from Gram-Schmidt to prove the Cholesky factorization. Thank you very much.